Okay, let's dive into this. Welcome to our Masterclass Explainer on Cambridge Computer Science Exam Strategy. Today, we're zeroing in on Cambridge AS and A-Level Syllabus 9618, specifically Topic 3.2, Logic Gates and Logic Circuits. Honestly, I call this topic the John Wick of the syllabus. It is literally the boogeyman of grades. When candidates are pushed out of their comfort zone with a massive, twisted circuit diagram, they usually just freeze up. But today, we are going to learn how to push back. And we're going to push back with perfect, examiner-approved answers. Let's set the stage with a real-world exam scenario. Think of a complex past paper question, like those notorious ones from the older 9713 or current 9618 papers. I want you to picture two students taking this exam. First, we have Alex. Alex is a hard worker, but Alex overloads their paper with raw computer science facts, dumping every truth table they've ever memorized, completely lacking any real analysis. Beside them is Sam. Sam actually knows the material, but Sam rushes, entirely missing the specific command word requirements like evaluate or justify, and just writes down a final binary output. Both of these students leave the exam hall feeling confident. Both of them are going to be shocked when they see their papers bleeding red pen marks. The difference between a B and an A-star doesn't come down to sheer memory. It's about understanding the rigorous underlying mechanics. It's about decoding exactly what examiners are demanding.
So here is our exact battle plan for today's explainer. First, we'll unpack the A-star difference. Second, we're going to outline the technical methodology you need. Third, we'll cover the top 3 examiner warnings. And finally, we'll wrap up with evaluation and exam strategy. Let's move right into Section 1, the A-star difference, moving beyond rote memorization in Topic 3.2. Now, we need to talk about what truly separates an average student from a top-tier candidate. It comes down to comparing superficial breadth with analytical depth. Let's look back at Alex, our first student. Alex uses superficial breadth. When given a complex scenario, say an automated greenhouse system requiring temperature and humidity logic checks, Alex just memorizes raw facts. They draw out the standard shapes for AND, OR, and XOR gates, they write out standard truth tables, but when it comes to applying those facts to the greenhouse scenario, nothing. Just a wall of memorized text. Examiners hate this. Now, contrast that with analytical depth. This is the systematic analysis and evidence-based reasoning that top candidates use. A student using this method looks at the same greenhouse problem, identifies the specific inputs, traces the logical flow through intermediate gates, and justifies why an XOR gate is the only valid choice for the boundary condition given. They don't just know what the gate is, they know why it has to be there. The Cambridge Assessment Framework actively prioritizes this depth across all computer science syllabuses, from IGCSEs like 0478, 0983, 0984, and 2210, all the way up to A-Level 9618. Memorizing facts is just a baseline. It caps your potential at a B grade. Analytical depth, that literally unlocks the A-star. If you think I'm exaggerating, let's look at the absolute gold standard of proof, the Principal Examiner Reports. They explicitly state candidates referencing cross-topic connections achieve significantly higher marks. Listen closely to that, because it's a massive hint. You cannot treat logic circuits as if they exist in a vacuum. The theoretical architecture of a logic circuit rests entirely on cross-topic integration. If you're building a half-adder or full-adder circuit, you need to explicitly connect your logic gate solutions to binary addition, 2's complement representations, and actual hardware execution. When an examiner sees you seamlessly linking the logic of a NAND gate to the physical memory storage limits of an embedded system, their eyes light up. Showing that high-level cross-topic mastery proves that you don't just understand the what, you understand the how and the why. And that is exactly what earns the top marks on these papers. Before we continue and reveal the exact technical methodology to secure every single one of those marks, subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's jump into Section 2, the technical methodology. Specifically, we're talking about the method mark strategy. Here is a reality check. In Cambridge computer science exams, the final correct answer is only a tiny fraction of the battle. Examiners award the bulk of those crucial points for your process, the method marks. So the crucial point is how you structure that procedure. Top students use what we call the PEEL framework: point, evidence, explanation, link. Let's map that onto the 4 steps required to tackle complex logic questions. Step 1 is to deconstruct the question and extract the relevant data. This is your point. You identify the exact command word, like draw, state, or evaluate. Step 2 is to select your analytical framework. Are we using a truth table, a Carnot map, or Boolean algebra? This acts as your evidence. Step 3 is where you execute with clear standard notation. No messy scribbles, you meticulously show the intermediate outputs of every single logic gate. This is your explanation.
Finally, step 4 is to present with correct terminology. You link your technical findings back to the specific context of the question. Every single one of these steps is a distinct opportunity to earn a method mark, proving beyond a shadow of a doubt that your final answer isn't just a lucky guess, but the result of bulletproof logical reasoning.
Now, let's talk about the transformation. Remember Alex and Sam? Imagine them rewriting their answers using this technical methodology. This methodology extends deeply into what we call algorithmic thinking. In Topic 3.2, algorithmic thinking requires step-by-step decomposition. Instead of panicking at a massive logic circuit, you break it down. You isolate the first AND gate, you find its output, you label it, then you move to the next. Next, you have appropriate data structure selection, knowing how to extract binary representations correctly to feed into your logic trace. Then comes efficient code implementation, or in this case, efficiently drawing your logic circuit without redundant gates. And above all, rigorous testing. When you finish a truth table, do you just move on? No way. You test it. You run a dry run trace table using the edge cases to ensure your logic holds up. This is the complete start-to-finish life cycle of a top-scoring exam answer. When Alex and Sam apply this algorithmic thinking, the red pen marks on their paper literally transform into green check marks. They go from losing points on structure to locking in every single available method mark.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Moving on to Section 3. Top 3 examiner warnings. These are the critical traps to avoid in Topic 3.2. Listen up, because there are exactly 3 critical, grade-destroying mistakes that students make year after year. The rule of 3 is incredibly powerful, and I want you to burn these specific traps into your memory so you never, ever fall for them on exam day.
Now, what's really interesting about these mistakes is that they usually aren't about a lack of knowledge. They're almost entirely about a lack of precision. Let's do a quick interactive workshop right now. Imagine a 60-second timer is ticking down. Mistake number 1, using the wrong algorithm for the context. I've seen students try to use complex Boolean algebra simplification when the question explicitly just asked for a simple truth table logic trace. They waste 10 minutes and get 0 marks because they didn't scan the data properly. Mistake number 2, forgetting to check boundary conditions and edge cases. Let's say you write a paragraph explaining a safety system's logic. If you don't evaluate what happens when all inputs are 1 simultaneously or all 0 simultaneously, your logic is fundamentally flawed. Examiners look specifically for those edge cases. And mistake number 3, answers that are not specific to the context given. If you have 30 seconds to speed write a Peel paragraph about a chemical plant's pressure sensors, you cannot just say input A and input B. You must write pressure sensor A and temperature sensor B. If you strip away the context, you strip away your marks. It's really that simple.
That leads us directly to a massive screaming terminology alert. Candidates consistently confuse key terminology, and examiners have absolutely no patience for it. There is a strict examiner requirement to explicitly define all key terms before utilizing them in extended responses. Think about command words. If a question says describe, you give characteristics. If it says evaluate, you must give strengths, weaknesses, and a justified conclusion. When discussing causal relationships in a complex logic circuit, you must use precise academic terminology. Please do not ever write that a gate changes an input or flips it. No. Say it inverts the signal or it outputs the logical NOR. Sloppy terminology is the hallmark of superficial breadth. Precise terminology, that proves you have that analytical depth we talked about earlier. Let's move into our final phase, Section 4, Evaluation and Exam Strategy. The ultimate trio: deconstruct, solve, evaluate. This brings us to the absolute highest tier of assessment objectives. When an examiner throws a curveball and asks you to evaluate alternatives or justify a specific logic circuit design, we have to ask, how do we effectively evaluate algorithmic quality under immense exam pressure? You can't just write down that one logic circuit looks better or runs faster. That's a 0-mark answer. When evaluating algorithm quality, examiners demand that you assess 4 specific criteria. First, time complexity. How efficiently does the logic execute as the number of inputs scales up? Second, space complexity. How much memory overhead, or in hardware terms, how many physical logic gates are required? Fewer gates mean less space, less power, and less heat. Third, edge cases.
How robust is the solution against extreme or unexpected boundary inputs? Does the system crash safely? And fourth, the overall effect on performance. If you want to absolutely dominate these papers, you construct your answers using these exact metrics. You decode the command word, you apply the Peel framework to structure your argument, and you use a time management matrix, meaning you never spend more than 1 minute of time per mark available. Comparing alternative approaches using these rigorous criteria provides exactly the kind of justified, bulletproof recommendations that Cambridge examiners dream of reading.
We've deconstructed the syllabus, we've exposed the examiner traps, and we've built a complete system for answering these questions. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. I want to leave you with one final thought. When you sit down for that exam paper, will your response rely on flawed, superficial memory, or will it be driven by the precise, strategic methodology we covered today? Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.